7.3 a one-tail test. We'll discuss this one with the example. The standard treatment for a particular disease has a 2/5 probability of success. A certain doctor has undertaken research in this area, has produced a new drug, and which has been successful with 11 out of 20 patients. Doctor claimed that new drug represent an improvement on the treatment. So then, so this is a standard story, treatment and improvement, and now the probability should be increased. So I will follow the format given in here. Formulate a model for the test. Formulate a model for the test. So the test is going to be X. We can define the test statistics. Number of patients in the trial or drug. Number of patients in the trial for whom the drug was successful. So this type of model will follow if P is the probability of success, so it will follow the binomial distribution in this type of model with N and P. So N value we know now, that is going to be 20 P. Now identify a suitable null hypothesis. Null and alternative. So we know that this is going to be H naught. It's given P is, this history is given. The standard treatment particular disease has 2/5 of probability of success. This is the data from the population. 2/5. This, which is 0.4. And then H1, now he believed that this 0.4 is increased in this case. Then P is increased more than 0.4. So we have to check the upper tail now. Next one is calculate the probability of the test statistics. Calculate the probability of test statistics. Take in the observed value. Assuming null hypothesis true, very important. Calculate the probability of the test statistics. So X, we will get X equal 11. So this is the observed value. So assuming the null hypothesis is true, so we can write assume H not is true. So X follow binomial. If it is true, they have to follow binomial 20 11. Sorry, 20 0.4. What is H naught? H naught probability is 0.4 according to the null hypothesis. So then if null hypothesis is true, that it should follow this probability. But P is telling, the alternative is telling, no, it can't be 0.4. It has to be more than that. So now you know that 0.4 probability for 20 behave differently, and it's more than that. Okay, let's say 0.5. So 0.5 probability behave differently. So we are going to trace that with the probability or number of with the observation, because this is 0.4 distribution. If it is more, it is 0.5 or 0.7, something like that. So then the location of these values is varying accordingly. According to this one, 5 is let's say 10 is here. According to 0.4, 10 is lies in somewhere here. Right? If you can't understand this one, just leave it for a while. Now the observed value x equal 11. So in the number line, so this is 10, 11, 12. Then you want to find the probability from right to left. You have to add everything. 20 probability, 19 probability, 19 probability up to 12 probability and 11 probability. So probability of x less than or equal to 11. So you can take this one 1 minus probability x. From total you are minusing this one less than or equal to 10. So from table you will see that this value is going to be 1 minus 0.8725, 0.8725, which is 0.01275. As a percentage, it's going to be this is 12.75. Then the other one is compare this to the significance level. So significance level is 5%. So then probability of x greater than or equal to 11 is 12.75. This one is greater than 5%. So 5% is here, and 12.5% here. From right to left, 12.5. It means this value not lies inside the critical region. So this is the critical region. So now it is outside the critical region. Hence we have to write the conclusion now. Hence now are we accepting or rejecting? We are accepting this one. But we write differently. Hence there are no sufficient uh, there is no sufficient evidence to reject H naught. So no reject mean what? Accept. That's how we write. We don't tell that hence null hypothesis is accepted. We don't write in that way for a reason. And we have to write the final answer for this. This is it is not accepting H or not. It is a test about the drug. So we have to give the conclusion that the new drug is no better than, hence the new drug is no better than old drug. Now in here you can see that this is method 1. So only method 2 also same setup, but instead of this calculation part, so we work with the probability here. Usually it is easy, but in terms of this one we can work out with the number critical values, critical value and the values in the critical region. So if you can find what are the values for this 5%, 11, 13, or whatever the values, and we will see that we will get that value in the critical region. So we'll adjust this part. In here now we have to do work out as usual the critical region like we did in the previous exercise. So this is page 205. Those are the cumulative distribution for 0.40 and n equal 20. And so we try with 13 first, up to 13. Probability of fx greater than or equal to 13 mean 1 minus probability of x less than or equal to 12. 1 minus 12 mean 0.9790. So this value is 0.021, which is 2.1 as a percentage. Yeah, we'll stay with the, yeah. Now probability of x will go one further, 12. Then 1 minus p, x less than or equal to 11. So this is 2.1%. This is less than 5%. The 1 minus 11, 0.9435 is going to be 0.0565, 0.0565. So this value is going to be 5.65% greater than 5%. Now it's clear that this is, if you go up to 12, it is more than 5%. If we go up to 13, it is less than 5%. So this is the immediate one. So the critical value is 13. So critical value is 13, and critical region is x equal 13. We write as into 13x up to 20. Now we calculate the critical region in terms of values. Now we want to compare to the significance level, or compare to the significance level, or compare with observed value. Observed value. Uh, since 11, that is the observed value, since 11 does not lie in the critical region. There is no sufficient evidence to reject H naught. Critical region, there is no sufficient evidence to reject H naught. The simple wording is accept H naught. We don't tell this one. Accept H naught. Hence, new drug is no better than old drug. So you can use either as a percentage, or you can find the critical region and compare with the observed value.